Hello and welcome to lecture 41. In last lecture, we were discussing about the construction of 3-spool turbofan engines, and we discussed about the construction of this 3-spool configuration, where we have observed like we will be having 3 different spools. One, that's what we say HP turbine, that will be rotating the HP compressor. We will be having intermediate pressure turbine, that will be rotating your intermediate pressure compressor, and LP turbine, that is what will be used to rotate the fan. And we were discussing about various advantages of 3-spool configuration, where we observe we will be having great control on mass flow rate as well as pressure distribution. That is what will be lead to improve the efficiency of the engine. We have observed by thrust to say power to weight ratio or thrust to weight ratio, that is what is been improved by using this kind of configuration. We have enhanced thrust because we have great control both in terms of aerodynamics, thermodynamics, that is what will lead to enhance the thrust. We have more durability and load distribution. Basically, we have 3 different kind of bleedings which will lead to give less stress on each components. These engines are faster in terms of say response compared to when we are observing say for 2-spool configuration, and this is incorporated with the advanced technology and its most modern design. We will be having wider operating range in terms of flying capacity, in terms of like flying speed, in terms of operation. We will be having wider range. At the same time, it is also providing us the compactness, because the number of components what we will be using, they are less, because here we are having the permission for rotating each wheel at particular speed. Suppose if we consider say HP spool, that will be rotating at the highest speed, intermediate spool that will be rotating at the medium rate, and we are looking for the fan or say LP spool that to rotate at the lower speed. So, that is what will lead to reduce the overall number of components requirement. At the same time, that is what will be reducing the overall size of the engine. But at the same time, we have counter argument in terms of increased weight compared to your 2-spool configuration. It is much more complex. You can understand, you can see the configuration where we are having say number of components, they are being arranged in a different way. If you recall, when I was discussing about the single spool turbojet engine, then we were discussing about say 2-spool turbojet engine. There people, they were hesitant to accept the kind of configuration or kind of multi-spooling. So, here we will be having 3-spool. So, that is what is more complex in terms of designing. At the same time, it is having say restriction in terms of accommodating for the special application where the space is a constraint. Much more complex in terms of maintenance or repair. You need to have the specialized training for repairing purpose, and it may take more time for say doing the maintenance work. That may not be accepted sometimes by its airline companies. At the same time, we will be having great constraints in terms of different design configurations. Since it will be having more number of components, so reliability, that will be the question mark. And we see like almost all engines which are existing running fine with all airlines, all kind of aircrafts, they are working fine with the 2-spool configuration, and that is the reason why like inclination towards the 3-spool, that is what was little people, they were having little complex to move towards the 3-spool configuration. No doubt what all benefits we are discussing, that is what is much more comparable compared to our 2-spool configuration. But universally, if the things are accepted with the 2-spool configuration, then people, they are little hesitant to move towards the 3-spool configuration. But over the year, the trend, that is what has changed. Now people, they are more comfortable to move towards the 3-spool configuration also. So, Rolls-Royce is the only company who are making 3-spool configuration engines. Then we were discussing about the cycle analysis. We have solved the numerical for the flying condition. Let us move towards the next. So, like this course, it is for aero engine gas turbine cycles. So, Let us try to look in a different perspective. Let us move with some other configuration. So, what all we were discussing, we have initially started with the single spool configuration where we were having unmixed configuration. Then we were discussing about say unmixed two spool configuration where we have discussed fan and LP compressor, they are on same shaft. Then we were discussing fan only will be on say LP. Then we started discussing about the gear turbofan engine where we have discussed what all are the advantages and what all are the challenges for gear turbofan engine. And in last lecture we were discussing about the 3 spool configuration. Now, let us move today towards say forward fan mixed flow 2 spool configuration. Here in this case it is been classified in two ways. One, it is mixed flow engine without afterburner and mixed flow engine with afterburner. So, you can understand when I say without afterburner and with afterburner means it has a special application. What will be that special application? Yes, you are right. When we say afterburner, that means this is having more application towards our fighter engines or fighter aircrafts. Let us look at what all we know. So, here in this case we were discussing about the turbojet engine and we realized the thrust generated, that is what is a function of mass flow rate into exit velocity. We realize in order to increase the thrust we have two options. One, it is to increase the exit velocity and second you can say to increase the exit mass flow rate. Now, if we look at suppose say very first with increase of exit velocity, that means at the entry of my nozzle I need to have high temperature because I am looking for expansion work with high enthalpy. That means I need to have higher turbine entry temperature and that is what was putting some constraints in terms of application. Suppose if we consider say very high turbine entry temperature, that is giving benefit in terms of improvement of thermal efficiency, but at the same time we will be looking for say special kind of materials which can be used for this kind of purpose. Later on, as the technology develop, this aircraft we were discussing say turbojet engines, they are very good in terms of supersonic flights and that is the reason why major attraction of using these turbojet engines are more towards the fighter aircrafts. Now, because of higher temperature we will be having IR signature, infrared signature. That is the reason why we will be easily identified by the enemies and there may be chances that we will be losing our fighter aircraft because by using missiles one can fire. So, that is the reason people they were looking for some other kind of options. So, let us try to look at what all options we have. One more option, it says like can we play with the mass flow rate? Now, for mass flow rate we are having two kind of configuration we were discussing. One in which if you look at this is my core engine or we can say that is what is my turbojet engine, and here in this case if we look at my LP compressor and fan, they are on one shaft and we will be having two streams of flow. You can say it is a primary stream of flow from where the exhaust from my turbine, that is what will be coming out. At the same time I will be having some other stream where my air will be bypassed through this fan. So, it is called bypass ratio engine. So, we will be having secondary stream and primary stream and that is what will be coming out at the exit. We were discussing about the benefits of this. Let us recall what all benefits we were discussing. Very first thing, that is what is in terms of increase of thrust, because we are increasing our mass flow rate to this engine. No doubt here the mass flow rate what we are discussing, it is low mass flow rate and my exit velocity will be higher, but you can say it is comparable, that is one. Second, if you look at here this stream what is coming out, secondary stream, that is what is covering my core engine, that will be helping us in terms of cooling of these blades and that is the reason why it is permitting us to move with the higher elevated temperature for turbine blades. So, that is benefit. Okay. Next, if you look at what gas that will be coming out from this core engine, basically for turbojet engine The big issue is higher exit velocity, and that is what was generating a lot of noise. Now, since it is been covered with my cold stream, that is the reason why it is suppressing the noise. So, that is also one of the benefit. Now, if we look at what exhaust, that is what will be coming out from the nozzle, it will be having some temperature, and that temperature can easily be identified in terms of IR signature. Suppose say if we will be suppressing that by using this stream, then it is helping. So, that is what has attracted the attention for using this kind of engines for military purpose. Then people slowly they start thinking of, can we further increase this mass flow rate? Basically, this mass flow rate in the sense, like this mass flow rate what we are discussing. Suppose say if I will be using this logic for turbojet engine, then I need to increase my frontal area, means my engine size will be larger. That is what is not permitted. So, let us move towards the other thought process. Here if we look at, we are having this as bigger size fan. Similarly, we will be having say this as my core engine, this will be my secondary stream. Okay. So, similar kind of thought process we have, but here if we look at, it says we are having higher mass flow rate and our exhaust velocity will be lower. So, thumb rule says almost 70% of the thrust, that is what will be generated by this bypass duct for this high bypass ratio engine, and that is what is lead to increase our propulsive efficiency. And as we are discussing again and again, our major interest is towards the overall efficiency, or we can say thermopropulsive efficiency. So, here we are getting benefit both in terms of increasing the thermal efficiency, at the same time we are able to increase the propulsive efficiency, and that is how we are increasing our overall efficiency. So, this is working absolutely fine with us. Now, let us look at, suppose if we consider here, say this is my core exhaust, that is what will be coming out from my core nozzle or say turbine nozzle, and here this is coming out from my say bypass nozzle, and they are separate. Now, let us think slight different. Suppose if I consider I will be making some arrangement in which the exhaust from the turbine and exhaust from this fan, they both will be mixing at some location, and after mixing that will be coming out from single nozzle. So, it says it is partial internal mixing kind of configuration. So, here let us look at what is the meaning of that. So, here if you look at, this is my core engine from where the exhaust, that is what will be coming out from the turbine, and at the same I will be having the exit that will be coming out from this bypass duct. They both will be coming here, that is what will be getting mixed. Okay. So, we will be having mixing of hot stream and cold stream. You can understand when I say mixing, that is what is happening. So, you can understand, say when the mixing will happen, I will be having this temperature that will be going lower, and with that temperature and pressure my flow will be entering inside the nozzle, and this nozzle, it is a single nozzle, not two separate nozzles. Here we will be having single nozzle, and from where the exhaust gas will be coming out. Now, let us try to understand what all is a benefit in terms of using this configuration. Let us try to understand. Suppose say you just think of what all are the benefits of this kind of configuration. What you feel? Just make a thought process. Yes, very first thing you can say, we are mixing our hot gas and cold air here, that is what will lead to suppress our IR signature. Okay, that is one thing. Second, if you look at, we are reducing the weight of this engine by using only single nozzle. Yes, that is second benefit. Here in this case, you can say this kind of configuration we can use for different engines, what all we have discussed. Suppose if you look at, do not get confused, here I can use fan or fans. this kind of configuration, I can go with low bypass ratio engines, I can go with medium bypass ratio engines, I can go with high bypass ratio engines. Okay. Suppose if we consider with the low bypass ratio configuration, yes, this is what is very much possible, where in order to increase your pressure, you will be having more number of fans which will be rotating at the high speed, because we are looking for high pressure exit that will be coming out from this bypass duct. What is the requirement? I want to mix that cold air with this hot gas. When the mixing will happen? When we will be having the static pressure to be same, or we can say when we will be having the exit velocity to be same, or in other language we can say when we will be having total pressure coming out from my hot stream and my cold stream, they both are same, then only we will be having the mixing that will happen. Okay. So, let us look at what all are the benefits in terms of using this configuration with what we say as a mixed configuration. So, here if you look at, this is the engine, okay, where you are having say all engine configuration, say fan, you will be having bypass duct, we will see the cut section, and this is what will be my single exhaust. Okay. So, what it says, like optimum fan pressure ratio for mixed flow configuration is lower than that of the separate flow for the given bypass ratio. Suppose say if you are taking say bypass ratio of 6 for both say unmixed and mixed configuration, for unmixed configuration we will be having this pressure ratio to be higher, and you can say for mixed kind of configuration we will be going with the low bypass ratio, because that is what is giving us benefit in terms of higher specific thrust. That is what is our requirement. It depends on what all will be our application of these engines. Okay. Here in this case, since my pressure ratio is lower, so you can say power required by the LP turbine that will be lower. It may be possible that you will be able to reduce the number of stages of LP turbine, and it is giving lot of benefits in terms of thrust gain because of mixing. Again, the problem what we were discussing in terms of noise, that will get suppressed. At the same time, since my number of components are reducing, so it says there is a reduction in the weight. At the same time, one more benefit, it says we are able to accommodate the reverse thrust. So, here if you look at in this bypass duct, we will be having this as a thruster, they are called reverse thruster, bucket type reverse thruster, or we can say door type reverse thruster. So, what will happen, say modern engines, they are having very high thrust generation capacity, because that is what is our requirement. Now, in order to braking during your landing case, you need to have sufficiently good braking system, which may not be possible only with the conventional braking. What these people they are doing here, like since this is what is generating my thrust, so bypass duct, they will be opening the duct, and through which they will be allowing the air to move in this direction. That is what will be acting as a reverse thrust, and that is helping us in terms of stopping the aircraft. So, many aircrafts now onwards, whensoever you will be sitting in the aircraft, and if you have chance to sit beside say window, you can see this kind of configuration. That is what is helping in terms of say stopping or braking the aircraft. Okay. One such engine, that is what is say very famous engine V2500, that is what was in collaboration with 5 different companies, say Pratt and Whitney, with Japan Aviation, it was with say Avio company. So, all those say Rolls Royce, they are having their contribution, MTU engines, they were also having the contribution. So, this is what is one of the promising engine, that is what was used for A320 for say medium range aircrafts. Okay. Now, let us try to understand what all are the applications of these engines. So, here if we look at, we have observed like we will be achieving the good fuel economy or fuel efficiency, we are able to achieve the higher thrust and lower emission, and that is the reason it is attraction for say military aircraft. When I say military aircraft, do not get confused. Very first classification we can say that is what is fighter aircraft. So, mixed flow configuration, it is used almost all fighter aircrafts, they are having mixed flow turbofan engine kind of configuration. The attraction is because of high thrust to weight ratio. At the same time, it is giving exceptional performance in terms of speed, maneuverability and climb rate. Fuel economy is also one of the crucial thing when we want to extend our flight duration. At the same time, we have observed, like, since we are reducing the emissions, that is what will be lowering the infrared signature, and that is the reason why this is major attraction for fighter aircrafts. Same way, this is also been used for strategic bombers, because we are looking for long range capability in order to carry out the mission. At the same time, we are looking for higher fuel economy at higher altitude, and it will be used for having say heavy payload, and that is the reason why this is what is one of the attraction. Okay. Same way, it is also been used for say transport aircraft. So, military transport aircraft, we are looking for fuel efficiency. Just remember one thing, when I say fuel efficiency, that is what is not straightway related in terms of fighter aircrafts, but when you are comparing with a turbojet engine, they are far better in terms of fuel efficiency. Okay. So, fuel efficiency is applicable for transport aircraft, where we are looking for long range durability. We want to have carry out say troops, equipment or supply over the long distance without say frequent refueling, where we will be having this kind of application. Same way, this aircraft engines are also being used for say maritime patrolling, for surveillance purpose, maybe for survey. It is also been used for anti-submarine warfare missions, where our major requirement is higher endurance and range. Now, these terminologies we have discussed in first week. So, again you just revisit that part. You can say the attraction for say mixed flow configuration is more in terms of fuel economy, it is more in terms of thrust, more in terms of endurance, range, all those stuffs, and that is the reason why this is what is one of the major attraction. Now, let us look at say we will be having the configuration, it is a low bypass ratio engine. When I say low bypass ratio, means we will be having bypass ratio in the range of say up to 2. So, we can say less than 2, that is what is. Okay. Now, the primary reason for this, it is to achieve higher thrust to weight ratio. We are having benefit in terms of speed and maneuvers. One major attraction is we need to accommodate this engine within the fuselage. When we want to accommodate that within the fuselage, where we are having limited space, that time we will be having this as one of the major attraction. At the same time, in order to have say high speed operation and quick maneuvers, this is giving the reasonable say thrust. At the same time, like for passenger aircraft application, where we are looking for higher specific fuel consumption, that is not beneficial in terms. But when we are comparing these engines with say high bypass ratio engines, then we will be having the specific fuel consumption that will be slightly on the higher side. So, based on what is our primary requirement, maybe in terms of agility, speed, say combat performance, and when we are looking for long range efficiency, this is one of the attraction. So, in overall we can say mixed flow turbofan engine with high bypass ratio, that is what is also been used for commercial airlines. They are also been used for say military purpose, like as we have discussed strategic bombers, transport planes. The engine priority for fuel economy and long range availability, that is what is suitable for the non-combat kind of applications. So, in overall, if you look at say low bypass ratio engine, it is been used to optimize the performance for combat scenario, where we are having say military aircraft, they are having application with high bypass ratio engine because of fuel economy and the range. So, basically the choice of these engines, it is depending on specific mission requirement and operation need for the aircraft. Okay. So, let us look at what is a construction of this. So, here in this case we have forward fan mixed flow engine without afterburner. So, let us put the station. So, initially we will be having inlet, we may be having fan or fans, it depends on what is the kind of bypass ratio we are selecting. Suppose say we are having low bypass ratio engines, that may be having maybe 2 or 3 fans. Suppose if I am moving towards the medium range, where we will be having 1 or 2 fans, it depends. Then that will be followed by the compressor, combustion chamber, HP turbine, LP turbine. Then we are having this as a mixing chamber. Then we will be having next component as a nozzle. So, basically our LP turbine, it is been used to rotate the fan or fans, and HP turbine, that is what is used to rotate the compressor. So, this is a kind of configuration, that is what we need to understand when we are discussing about the mixed flow configuration. Okay. So, let us look at how my flow will be on TS diagram. You can try, let us try to understand. Suppose if I consider this is my say entry condition, we are having say our inlet. So, my exit pressure is P02. Next component we have is our fan, that is what will be raising our pressure from P02 to P03. The next component what we have is our compressor, that is what will be raising the pressure from say P03 to P04. The component now we have is our combustion chamber. We have discussed the combustion process in gas turbine engine, that is what is not happening at the constant pressure because of losses, and that is what will lead to reduce or drop the total pressure. This will be in the range of 2 to 5% of the entry pressure. So, you can say this is my say turbine entry pressure and turbine entry temperature. Okay. Now, next we have is our HP turbine, that is what will be getting say expansion from P05 to P06. We have our next component, that is what is say P06 to P07, that is representing my expansion process that is happening inside my LP turbine. Now, let us look at what we have understood here. So, here in this case we can say this is my exit of fan and this is my exit from the core engine. They both are getting mixed here. So, now what will happen within that? So, as we have discussed, in order to have this mixing to happen, the conditions are very first thing, I need to have my static pressure at the exit of fan and static pressure at the exit of turbine, they both need to be same, or we can say exit velocity from the fan and exit velocity from the turbine, that need to be same, or we can say we need to have our total pressure to be same. So, let us represent that mixing process. What is my requirement? I will say my P03 and P07, they need to be same. So, you can say this is my constant pressure line, and because of mixing it will be attaining some pressure say P08, and because of mixing I will be having the reduction in temperature. Okay. So, I will be locating my point 8 somewhere here. It depends on what is my pressure and what is my temperature. Mainly pressure line is here, how effectively the mixing is happening, accordingly we will be having the shifting of this point along this line. Now, what is the next process? We have our expansion process which is happening inside the nozzle, and that process we are representing as say 8 to 9. Okay. So, just look at this cycle for the mixed flow configuration, our cycle, that is what is totally different from what all we have discussed up till now in terms of unmixed kind of configuration. So, be careful about this aspect. Okay. Now, here as we were discussing, in order to have this mixing, we need to have our static pressure and velocity to be same. We know since this is our duct, that may lead to some losses in terms of pressure. So, that is what has been represented here, losses within the fan duct. You may be having say loss here, and that is the reason why my P08, you can say my P03, P03 dash, P07 and P08, they all will be same. Then only we will be having proper mixing that will be happening, and this is must. That is the reason why this cycle is somewhat different from what all we have discussed up till now. Okay. So, let us look at the processes. Now, we have our all components. For this components, very first component we have is our inlet. This inlet we know we have our inlet efficiency or diffuser efficiency. Based on this diffuser efficiency, we can calculate what will be our exit total pressure. We also know what is our temperature at the exit of the intake, because that process we are considering as a adiabatic process. So, we will be able to calculate what will be our exit pressure and exit temperature from the intake. These things are known to you. Now, let us look at with the next component. What we have is say fan or fans. Here in this case, fan pressure ratio we can say it is P03 by P02. We have information about the fan efficiency we have discussed in our second week, from where at the initial stage we need to assume this efficiency value and what need to be the range of that. And this we are correlating in terms of efficiency and pressure ratio. That is what will be helping us to calculate what will be the temperature ratio, or we can able to calculate what will be the exit temperature from the fan. Be careful here in this equation, this is representing the polytropic efficiency of fan. It may be single fan, it may be multiple fan. So, this all will be having different maybe polytropic efficiency. So, that is the reason why this is what has been considered here. Now, let us look at the next component, that is our say compressor. This compression ratio we know it is P04 by P03. We have our isentropic efficiency of the compressor, which we are correlating in terms of pressure ratio and temperature ratio, based on which we can calculate what will be the pressure and temperature at the exit of our compressor. Now, in order to understand say combustion chamber, for this combustion chamber we know we can take the control volume. So, the heat input we can say it is m dot core into H04. This is the amount of fuel what we are inputting, it is mf into Cv based on my combustion chamber efficiency, and this will be the exit from the combustion chamber, or that is what will be going to my turbine. We know in combustion chamber we will be having the drop of pressure, and that is what we are correlating in terms of pressure drop in combustion chamber. So, let us put the energy balance. When we are putting our energy balance, we are able to calculate what will be the fuel air ratio for this engine. Okay. Now, the next component what we have is our HP turbine. We know this HP turbine we are using for say rotation of say compressor. So, we will do our work balance of HP turbine and the compressor. When we are correlating that, we will be having say ratio of the temperature. Based on that temperature ratio, we can calculate what will be the exit temperature from the HP turbine. We also want to calculate what will be the pressure. So, we have the formulation of efficiency. This efficiency we can correlate in terms of pressure ratio and temperature ratio. Based on that, we can calculate what will be the exit pressure and exit temperature from the HP turbine. Okay. Let us see, we have our LP turbine. Similarly, we can write down this LP turbine mainly been used to rotate our fan or fans, and if we put this balance, you can say it is mCp delta T0. Here this is m dot core into 1 plus F. Similarly, in terms of what flow rate it is at the input, that is given by 1 plus beta into m dot core Cp delta T0. Based on that, we can calculate what will be the exit temperature from the LP turbine, and based on isentropic correlation, we can calculate what will be the exit pressure from the LP turbine. So, this is the case what we are looking for. Now, up till here what all we have discussed, that is what is in line to what all cycles we have discussed up till now. Now, the change will come in terms of our understanding. Let us see. What we have is our mixing chamber. What is the input to my mixing chamber? I can say one, that is what is coming from my fan, that is what is say energy, that is what is coming out from the fan. This is what is the energy, that is what is coming out from my core engine or from the LP turbine, and they are getting mixed and it will be coming out at H08. Now, let us look at in terms of say our first law of thermodynamics. We can say our H03 plus H07, that is what I can write down as H08. What is our H03? So, this H03 we can write down, it is MF into Cp into T03. Similarly, for H07 it is 1 plus F m dot core Cp T07, and here in this case we will be having say rise of temperature, it is T08, and that is what is been represented in terms of this plus this. Now, let us try to calculate here. So, here in this case if you look at, since I will be having mixing, that is what is happening in this mixing chamber, that is the reason why here in equation I have written Cp8. Okay. Similarly, here also I have written Cp8. Now, those properties after mixing will be changing, means my specific heat will be changing, my specific heat ratio will be changing. So, in order to do that calculation, conventionally universally people they have adopted with mass average property for these gases. It says my Cp at exit will be Cp7, that is what is coming out from my say turbine nozzle, plus beta into Cp3, this is from say my air divided by 1 plus beta. Similarly, the value of R, that also will be R7 plus beta R3 divided by 1 plus beta. Specific heat ratio is gamma 7 plus beta gamma 3 divided by 1 plus beta. Now, once we have this information, we have our question, where is my temperature T08, and this T08, that is what we are calculating based on what energy balance we have. Okay. So, you can simplify this equation and you will be getting this as your requirement. Okay. Now, let us look at what is happening in terms of pressure. So, maybe within this mixing chamber we will be having drop of pressure. So, that is the reason why my pressure at the exit of mixing chamber, it is important. So, we can calculate what will be our P08, we will be calculating what will be our T08, because that is what will be the entry condition for our nozzle. So, let us look at here, it says for mixing chamber, this is represented in terms of mixing ratio. It says that need to be less than 1. Conventionally people they are accepting that number as 0.98. So, there will be 2% drop, that is what is happening in this mixing process. So, if you recall, when you have studied your basic thermodynamics course, when we were discussing about say steady flow energy equation SFEE, where we were discussing about all these components. So, one of the component, that is what is coming as a mixing chamber. So, in terms of understanding what is the use of that is what is not been taught in a proper way. We say okay, we are having say one end we will be having say water, that is what is coming, other way water, that is what is coming, and in total it will be coming out. That is wrong. Just realize this thing. This is what is the actual application of what thermodynamics we are discussing at this moment. Okay. Now, this will be giving us idea about what will be my temperature, exit temperature, what will be my exit pressure, and what will be our specific heat ratio, and what will be our Cp value. Now, once we have this information, we will be going with say component that is called nozzle. So, for nozzle now we are having single nozzle. So, for that single nozzle we will be calculating our critical pressure ratio. For that, just look at the change in the equation. Here this is my nozzle efficiency and this is gamma 8, that is what is the specific heat ratio after mixing. Similarly, here this is what is gamma 8. Be careful when we are discussing say mixed flow configuration, we need to be very careful in calculation here. So, we have two cases, we can say whether my nozzle is choke or unchoke based on our critical pressure configuration. This is what is known to you. When we are having critical pressure, that is what is less than my atmospheric pressure, then my exit pressure will be atmospheric pressure. Based on that, we can calculate our static temperature, and that static temperature we are using for calculating our exit velocity. Similarly, when we are discussing about say our nozzle, that is what is choke condition, my critical pressure will be higher. So, my exit pressure will be critical pressure. Based on my temperature ratio correlation, we can calculate what will be the static temperature, and from that static temperature we will be calculating our exit velocity. Okay. Be careful here, this is gamma, here R also is R8 and T9. Okay. So, this we can say based on all these parameters we will be reaching to calculate the performance parameters. Now, this is similar to what all we have discussed for our turbojet engine. Just look at the formulation, because we are having single exhaust nozzle. So, we can say this will be m exit into V9 minus m infinity into V infinity, plus this is what we are writing as P9 minus P infinity into A9. My exit mass flow rate, we need to be very careful here, that is what is say m dot core plus m dot f plus this mf, and that is what we are writing as a 1 plus beta plus f into m dot core. Be careful here, it is specifically been mentioned, here we are writing in terms of say what is coming out from my core, it is 1 plus f into m dot core, and here this is what is coming beta into m dot core. Do not get confused, that is the reason my exit will be like this. And my thrust specific fuel consumption we are writing in a similar way, m dot f divided by my thrust. Propulsive efficiency, that is what we are writing in terms of T into V infinity divided by T into V infinity, plus this is my exhaust loss. Okay. Same way we can calculate our thermal efficiency based on the numerical, what is the amount of heat we are putting, its output divided by our input. And once we have all this information of propulsive efficiency and thermal efficiency, we can calculate what will be the overall efficiency of this engine. Now, here this is what is something different, where you will realize we have bypass ratio engine, but this is what is working in line to say the turbojet engine. Though we are having bypass duct, we have single nozzle. Okay. So, just do practice for this plot of TS diagram, even you can do practice for this engine, and based on that you just try to derive the correlation what all we have derived. Now, in next lecture we will be discussing about one of the numerical, that is what will be building the confidence in terms of solving the cycle analysis for this kind of configuration. So, here we are stopping with. Thank you very much.